is an illustration of the active set algorithm works. So I have generated a reasonable instance of the quadratic programming problem. We have 5 optimization variables, and here we see the individual iterations. By the way, we have 5 optimization variables. We have something like 20 constraints. The total number of all possible combinations to be explored is something like 1 billion here. 1 billion iterations would be needed if we would just employ the brute force way. If we do it using this active set logic, we only need to perform 15 iterations. Okay? So how do we start this? We start with an empty set, empty active set, and we solve that system of linear equations. We find out that there is an improving direction, but we cannot go all the way of the direction with step length equal to 1 because we would violate some constraints. Actually, the first constraint that we would violate on our journey from x0 towards or in that direction is constraint number 2, and its distance is 0.24. Okay? So distance 1 would mean all the way to x plus delta. Okay, so this kind of like we can only go 24% into that direction. We hit constraint number 2. So we add constraint number 2 to the candidate active set, and we do the same again. Now, since we have a candidate active set, we are solving a problem with equality constraints. Solving a problem with equality constraints is easy. So we solve that easy problem, and we find out that there is an improving direction. However, we cannot choose step length equal to 1 because we would violate constraints. We would actually violate several constraints, but the first one would be constraint number 4. So we add constraint number 4 to the candidate, and we do the same. So we are adding constraints 6 and 10, 12, 14. We come here to this iteration, and we find out that we can no longer improve. The delta is 0. However, one of those lambdas is negative. And it's a lambda which corresponds to constraint number 12. So here, notice that the algorithm said add constraint number 12 because I think it will be in the optimal set. And here we came and said, oops, we made a mistake. 12 is not in the active set. So we are removing 12, so that's the candidate. We solve it. We find an improving direction. And actually here we are, for some reason, considering negative 1. This should not just consider 16. It should just remove that one. So we come here, again, no improvement, but still no optimality, so we have to remove constraint number 8. Here, there is an improvement with a unit step, meaning x plus delta satisfies all constraints, so we just go all the way into that direction. We come and we said, okay, so here we have yet a new improving direction. We need to remove constraints. And we do this until we get a solution which is both feasible as well as satisfying that the dual variables are all non-negative. And then we have found an optimal solution which we have 1, 2, 3, 4, 5, 6. Oh, it's actually 7 optimization variables. And it's actually the same solution that we would obtain by using the quadproc solver. Actually up to some rounding, but that's technically speaking -1. Okay. So this is how the active set method works on an example, and actually its implementation is extremely simple. It's, I don't know, 10 lines or maybe 20 lines, not really a big deal. So it all starts essentially here, and it's a bunch of comments that you can see here. So we start from some feasible initial point. I have just chosen 0. 0 does not always have to be the feasible initial choice. You have to be actually careful here. That is just a bunch of MATLAB math. And here is where the fun begins. Okay, so we form the KKT system exactly as we had it on the whiteboard. We solve the KKT system. We take the improving direction, which is called du. We take the Lagrange multipliers, and then we look at whether the improving direction is 0 or not. If it is 0, then we know that we are in 2 situations. Either all Lagrange multipliers are non-negative. We know we have the optimal solution. Or some Lagrange multiplier is negative. So here we look for the most negative entry and we remove it from the set. And we continue with the next iteration. However, if there is an improving direction, then what we do is we calculate all those distances. I have them here. If no constraints would be violated by going all the way to delta using unit step lengths, we just set the step lengths equal to 1. Otherwise, we have to choose it as the minimum among those values of the distances that we have computed right here. So yeah, it's 100 lines, but maybe 50 of them are comments and 20 of them are not really necessary. So maybe 20 lines of MATLAB code and probably something very similar for C. So this active set method is really something which is really simple, and it is used frequently in practice. And yes, you can argue, like, is the heuristics which says remove the constraint which has the smallest entry of the Lagrange multiplier, add the constraint which has the smallest distance. Are these really the best rules for a particular problem? That's why solvers, meaning software packages which implement the active set method, that's why they give us kind of the freedom to play with these kind of rules. And actually, different rules can then lead to different performance of the solver. But internally, this is what the active set solvers are doing. They don't solve the KKT systems in a brute force way. That would be a disaster. You never want to do that in a brute force way. Instead, they set up a set of clever rules which say how to update the candidate active sets such that we potentially arrive at the optimum in a fast way. In the worst case, even this algorithm would need to go through all possible combinations of active sets. So the worst case performance is bad. It's exponential in the dimension of the problem. However, in practice, these kind of algorithms are efficient enough to solve optimization problems with hundreds up to thousands of optimization variables. Especially, they are very good for application to optimal control problems because they are really easy to implement in the control hardware, and they are also quite fast. Essentially, all we are doing here is we are doing a matrix inversion because we have to find the improving direction. And that's done by solving the KKT system, and that includes matrix inversion. All other math that is contained is really simple. No big deal with respect to the software implementation of such an algorithm. However, I doubt that anybody of you would ever implement the active set method manually, though it's a very nice practicing exercise. Instead, what you would probably do is use some solver to solve these kind of problems. There are actually many software packages for quadratic programming. In MATLAB, we have QuadProg. It actually implements 3 different ways of solving quadratic optimization problems. One of them is the active set method. And we will cover one more in the next lecture. That's called the interior point method. You have to be careful, however, about the input format, which is actually very similar to the input format of LimProg. So essentially, we can provide separately the equality and inequality constraints as well as lower upper bounds on optimization variables. And that's the input. So we have to provide the Hessian. Notice that what QuadProg solves is 1/2 of the quadratic term. You have to be aware of this. We will see that in those applications in a second, that we have to actually create this Hessian with the knowledge of that QuadProg would further divide it by 2. Okay, so that's the Hessian, that's the linear term. We have inequality constraints, equality constraints, lower upper bounds. Similarly to LinProg, if you don't want, for instance, equality constraints, but do want lower upper bounds, you put empty matrices here. Okay? And the outputs are the same as in LinProg, and even the status flags, they mean the same. So similarly, as in linear programming, the problem could be infeasible. I mean, there is a relation between quadratic and linear programming in the sense the constraints are the same. So even in quadratic programming, the constraints could be infeasible. And we can even have an unbounded problem. 0 means maximum number of iterations is reached. So for those active set methods, we usually put a bound on the number of iterations because we know that the total number of possible active sets is huge. And usually if you need to do huge number of iterations, it means your problem is badly posed. Okay, so there is an internal limit on the number of active set iterations. So if you get status 0, it means numerical problems.